All right. Well, today I'm going to kind of go over some of the lab stuff with you here. Now, I'm just going to briefly go over it and hope that you're going to work on it. I'm going to give you some data files to use if you want to use those data files. But in general, we're looking at this mass spring damper. So we've done the mass spring damper a bunch of different times. You have too. I'm just saying you have done it a lot of times. I'm hoping that you can see that. I'm still struggling with my lightboard here. M, K, B. Okay, we're good for that. And so we've got our equations of motion, but one of the things that we know is that if we just look at remember I showed you how to make gravity disappear, so we're going to say Z equals 0 at equilibrium. And what I'm going to do is I'm going to, for each, what I'm going to do is we're going to try and make this X versus force, right? So we've got the X versus force, and we're going to take 1 point. So it turns out that in the mass spring damper system, you're probably okay just using one single data point. But I'm asking you to do 3. I know we didn't have, I didn't have the scale wasn't working. It's not my fault. They kept putting that scale back in the wood shop. You guys tell them to get that scale out of the wood shop. But I'm asking you to do 3 data points, and I'm going to show you why I'm asking you to do 3 data points. It just makes it easier so that there's not any kind of like extraneous stuff. That's not a very good color. I got to get some brighter colors here. I don't know what the deal is here. But one of the things is that I'm hoping that you'll find, I'm hoping that with those things that you're going to see that there is it turns out that it takes a little bit of force to move those springs. We'll talk a little bit about that later. But the bottom line is that what we're going to be looking at here is that we're looking at if the slope is equal to delta F over delta X, and that is equal to K, the spring constant. That's what we're trying to find experimentally. And once we find it experimentally, then we should be able to predict the natural frequency. So we're going to predict the natural frequency. Omega n is equal to the square root of K over M. And so hopefully we'll be able to find that clearly enough. And then the way we're going to find that is we're going to grab a hold of this thing and we're going to move it by some, we've got the equations, we've got the analytic solution. We're going to move this by some initial condition Z naught. We're going to move it by some initial condition Z naught. We're going to let it go. It's going to wobble. And what we're going to do is we're going to count 1, 2, 3. We're going to count however many of those we need to count. And we're going to find out what the period is. It's cycles per second. So it's the number of cycles over the number of seconds. Hashtag cycles, hashtag seconds. Okay, put those in your Twitter, whatever.
All right, so we're ready to go with our experiment. We have our spring. I've started with a red spring here. Got little hooks there, so we're going to put it down. Let me go ahead. I've got my physics toolbox suite going. Let's see if okay, so that makes it start recording. So let's start it recording here. We're going to see it's about 4 centimeters. 4, so let's start it with like a 2 centimeter start. Ready, go. So now we're taking data. Right? We don't really even have to count on this one. And I've chosen the slow one to do it at, right? So, okay, so then we can start.
MATLAB. We're going to go back to MATLAB, and we're going to make a vector of time. Time is equal to 0 by some delta t to some t final. So we're going to have a vector of t that's 0 to delta t by some final. And we're going to have the analytic solution that says x is equal to, and it's some kind of thing like x naught cosine of omega n times t. So, right, so you're going to just put that in, and then you're going to plot it. You're going to say plot t, oops, I'm going to get rid of that, t, comma, x, right? You're going to do that. All right, so then you'll have your little plot there, and then we want to go back through, and we want to just make sure that we know how to do numerical analysis, so we're going to do some Euler integration. We're going to just use the easy three-step method. I don't know if it's three-step, I just made that up. But we'll see how it is. It is that x dot is equal to minus k over m times x of k plus 1. Oh no, x dot of k. Right? So we found that by solving the equation. F is equal to mx double dot plus bx dot, which f was equal to 0. So we're looking at mx double dot is equal to, oh, sorry. Oh, geez. I do everything wrong the first time. This is what the bad thing is. I have to erase that kx, right? That's what we have, because b is equal to 0 in this case. So we're going to do mx double dot is equal to minus kx. So we know what the acceleration is dependent on whatever the x is, because f is equal to 0. So that's this equation. So we've got that equation. That's fine. And now what we're going to do is we're going to integrate that. We're going to say x dot k plus 1 equals x dot of k plus x double dot of k times delta t. That's Euler integration. That gives us the velocity. And now we're going to do that one more time. We're going to say x of k plus 1. We're going to integrate that one more time. That is x of k plus x dot of k times delta t. I'm going to ask you to do x dot of k times delta t. So that's what I say. It's an easy three-step method. 1, 2, 3. Three-step method. Okay, then we have to put like a loop. You have to put a whole bunch of different stuff in here. Like, that's not as easy. You have to have t final. We have to say t equals tk plus 1 equals tk plus delta t. We have to say k equals k plus 1, blah, 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 blah. And you'd have to put some and MATLAB always likes it. I read something that MATLAB, if you don't put that semicolon there, like, no, uses up too much memory. That's fine. We don't care about memory. We're not computer people, so we don't care. All right, so then the whole point of it is that we'd like to be able to compare. We'd like to be able to compare the analytic response. I think I drew this wrong. I drew it as a sine, and it should be of a cosine, but that's okay. That's what our analytic one is with our numerical simulation. We're going to put little x's there, numerical simulation. And we'll see how well they match. They should match it exactly right. Plus, we already have done it experimentally, so we should know that 1, 2, 3, we should know how that works and be able to prove that mathematically. Okay, yes, we have proved that it works experimentally. Now, I'm going to show you a picture. I'm going to show you a video where I've used the Physics Toolbox Suite to get the acceleration data. All right, so what is the acceleration data? So the acceleration data is that x double dot is equal to, let's start at the beginning. X equals a cosine omega t. That means x dot is equal to omega a. Derivative cosine is minus the sine. There's a minus sign there. Sine omega t. And then x double dot equals minus omega squared a sine omega. Doggone it. It's so hard to erase this stuff. You guys will appreciate it. Cosine of omega t. So this is what we measured. Hey, we measured this. I don't know if this is falling off the edge or not. I'm going to have to look and see. But hopefully we measured that, right? And so what we need to do, if we're going to measure that, if this is what our data set is, if we have there's an offset here, and I think the offset goes plus theta 0. I have to go, we'll have to figure all that out here. This is time. And so what we see is that, oh, it's a cosine term. It's still a cosine term, right? So this is what we measured from Physics Toolbox Suite. Now, how do we compare that with our analytic response? Well, we have to integrate this one time. Integrate, oh, I used F instead of the integral sign. I'm going to integrate this. Integral of x dot is equal to x dot. And now I'm going to integrate again. Integral of x equals x. So we can integrate it twice. Now I'm going to tell you there's a lot of problems with integrating. If you know how to integrate this so you get the right answer here, patent it, because you'll be famous and rich. Okay. But what we can do with this one is we can differentiate it. We can differentiate it, and we know how to differentiate it. X dot equals x minus x old over delta t. And then we can differentiate it a second time. X double dot equals x dot minus x dot old over delta t. Right? So we can do that twice, and then we can just plot this analytic expression. So we have an analytic expression, we've differentiated it twice, and we say, how well does that respond? How well does that match what we got in our Physics Toolbox Suite? And so we're going to plot those two things together in MATLAB. That's what our point is. So always with theoretical results and analytic results, we want to be able to put those together. Okay.